Welcome to AI and Machine Learning Deep Dives. Today we're tackling one of the most powerful algorithms out there, gradient boosting. If you've ever wondered how a model can actually learn from its own mistakes to get scarily accurate, well, you are in exactly the right place.
Today, we're going to break down how gradient boosting really works for classification. This is a powerhouse technique that you'll find everywhere, from predicting what customers will buy to absolutely dominating data science competitions. We'll start with the big picture, then walk through every single step of how the model is built, and finally, we'll cover its real-world power and pitfalls. Okay, let's get started.
First things first. To really truly get a feel for gradient boosting, we have to start with the concept it's built on, and that's ensemble learning. At its core, this is basically the idea that teamwork makes the dream work, even for algorithms.
So at its heart, ensemble learning is all about teamwork. The idea is that you can take a bunch of simple, kind of weak models that aren't very good on their own, and you combine them to create one super strong model that is incredibly accurate. It just goes to show that a lot of simple models working together can be way smarter than one single, overly complicated one.
Now, ensemble learning isn't just one thing. It really has two main flavors. First, you've got bagging, which you see in models like Random Forest. That's where you build a bunch of models independently and then just let them vote on the answer. Think of it like a democratic election. But then you have boosting, and that's what we're here for. This is totally different. It's a sequential process where each new model is built specifically to fix the mistakes of the one that came before it. It's less like an election and, honestly, more like a relay race, where each runner passes the baton and tries to improve on the last lap.
So, how does a gradient boosting model get started? It all begins with one simple initial prediction for every single data point we have. It's got to start somewhere, right?
To make this real, let's use a fun example. Imagine we want to predict if someone loves the famously awful but amazing movie Troll 2. Let's say in our little data set, 4 people are fans and 2 are not. Now, for a classification problem like this, the model can't just start with a simple average. No, its first guess has to be something different, the log of the odds.
And the math here is actually pretty simple. It's just the natural log of the number of people who love it divided by the number who don't. So that's the log of 4 divided by 2, which gives us about 0.7. And this one number, 0.7, becomes our starting prediction for every single person in the dataset.
Of course, log odds isn't super intuitive for us humans to think about. So the model immediately converts that value into a probability using the logistic function. And in this case, that initial 0.7 log odds just so happens to translate directly to a 0.7 probability. So the model's first, very crude guess is that everybody has a 70% chance of loving Troll 2. And that brings us to takeaway number 1. Gradient boosting for classification starts with a single prediction for all data points, the log of the odds, which is then converted to a probability.
Obviously, predicting the same 0.7 probability for everyone is a pretty lame model. We know for a fact it's wrong for at least 2 people. The real magic, the secret sauce of gradient boosting, is how it learns from those first mistakes.
We measure our error for each person by calculating something called a pseudo-residual. It's super simple. It's just the actual outcome, so 1 if they love the movie, 0 if they don't, minus our predicted probability. This residual tells us exactly how far off we were and in which direction.
And this right here is the absolute core of the algorithm. This is the whole game. We don't build a new tree to try and predict the original outcome again. Nope. Instead, we build a brand new decision tree specifically to predict the errors from our last step. This new model is obsessed with one thing and one thing only: fixing the previous model's screw-ups. Okay, now we hit a really crucial step. Remember, our main prediction is in the language of log odds, but the errors we just calculated are in the language of probabilities. You can't just add them together. So we need this special formula, which acts like a translator. Its job is to take the errors from our new tree and convert them back into the log odds format. This is the key that makes sure every new piece of information improves the model in a mathematically correct way.
So here you can see it in action. For the people who love the movie, the error or residual is positive, right? Because our 0.7 probability was too low. For the non-fans, it's negative. That fancy transformation formula then spits out the leaf output, which is the exact amount of correction the model needs to apply for each of those groups. And that brings us to takeaway number 2. The algorithm learns by building sequential decision trees that predict the errors or residuals of the previous model's predictions.
All right, so we have our initial guess and our first error-correcting tree. Now let's look at how these pieces combine, one step at a time, to build the final, really powerful model.
Now, here's a really crucial detail. The model doesn't just add the full correction from the new tree. That would be way too aggressive, and it would probably lead to overfitting. Instead, it scales that correction by a learning rate, which is usually a tiny number, like 0.1. This forces the model to take small, careful, little baby steps towards the right answer, which makes it much more stable and accurate in the long run.
So this entire process is just a loop, over and over again. We start with our log odds, we add a tiny piece of the correction from tree 1. Then we calculate the new, smaller errors. Then we build tree 2 to fix those errors, add a small piece of its correction, and on it goes, sometimes for hundreds or even thousands of trees. And that brings us to takeaway number 3. The final model is an additive combination of the initial guess and all the sequentially built trees, each scaled by a learning rate.
Okay, understanding the theory is great, but let's talk about why this algorithm is such a beast in the real world. And, just as important, what you need to watch out for when you actually use it. I mean, gradient boosting is famous for a reason. It consistently delivers what we call state-of-the-art accuracy. It's always at the top of the leaderboards in competitions. It's also incredibly flexible. You can tweak it for different kinds of problems, and it often just handles missing data in your dataset automatically, without you having to do a bunch of cleanup first.
But it's not a magic bullet. Because it's so obsessed with errors, it can be really sensitive to outliers. Just a few weird data points can throw the whole model off track. And if you let it build too many trees, it'll start to basically memorize your training data and then fail on new data. That's a classic case of overfitting. And yeah, it can also be pretty slow and computationally expensive to train.
So getting the best performance out of gradient boosting means you have to become a bit of a master tuner. These 3 parameters are your most important dials. N-estimators is how many trees you build, learning rate is that small step size we just talked about, and max depth controls how complex each individual tree can get. Finding that perfect balance is the real art form here. And that brings us to takeaway number 4. While powerful, gradient boosting's performance is highly dependent on tuning key parameters like the number of trees, learning rate, and tree depth to balance accuracy and prevent overfitting.
All right, that was a whirlwind tour. Let's just do a quick recap of the 4 key takeaways from this explainer, just to make sure everything is clicked into place.
So let's put it all together. First, we saw that it all starts with a single, smart initial guess for all our data, the log of the odds. Second, it learns sequentially, building each new tree with one mission, to fix the errors of the last one. Third, the final, super-powered model is built by adding up that initial guess plus a small, careful contribution from every single tree it built. And fourth, to unlock all that power, you absolutely have to tune its parameters carefully to get the best results without overfitting.
So I'll just leave you with this final thought. The entire strength of this incredible algorithm comes from its relentless, methodical focus on identifying and correcting its own mistakes, one tiny step at a time. It really makes you think, if that's how a machine achieves excellence, what does that say about the best way for us to learn?
That's all for now, folks. Please like, share, and subscribe for more like this.